is very important thing you want to do. Okay. Now, if you have quantitative data, how do we usually display it or organize our information? There's a quick way to do this if you have very few pieces of data, right? This is called dot plot. You just make a dot for each piece of data you have. So we have 7, we have 6, we have 8, then we have another 7. So if you have another data, you just stack on top of it, all right? And just accumulate these data. And then after you down the chart, you see the distribution pattern. Right, so that's called dot plot. Right, so that's group 1 dot plot and group 2 dot plot. Okay, just make a dot for showing one piece of data, right, at a time, right, and display them. Okay, so that I think it's pretty easy. Okay, and we talk about stem and lead plot. Okay, when you have quantitative data, usually the leading digits we're using the stem, and trailing digit we're using this lead. Okay, so we saw this example. This example, we want 2-digit data, right? So the leading digit is very simple, right? We have data range from 20 to 80, so we use 2, 3, 4, 5, 6, 7. We don't leave any gap, right? These are the leading digits, right? Range from 2 to 8. Then we put in the second digit, right, to actually start organizing the information. We have a 27, put a 7 as a lead for those 20s, right? And 50 and 33, and just keep building it out. I think you all know how to do this. So that's a stem and lead plot. And usually we will sort those numbers within each stem, right? So we get a ordered or sorted or ordered stem plot. Okay, so that's simple. And this is a chart also can allow you to see detailed information for each piece of data. And you turn it 90 degrees, you see a pattern, right? We have a distribution that mostly around 20 to 50 and then few in 80s, right? So they're outstanding data. And if we have 2 categories of numbers like this, data, right, we can actually do a so-called a side-by-side stem plot to do visual comparison, right, for among these 2 groups, right? So we do one stem for male, one stem for female. That's good, but we can actually merge them together. So that's easier for us to compare these 2 categories of data. Right, numeric data. Right, so that's easy. I think you all done that before. Okay, that's a very useful one. And dot plot and stem plot usually, in the beginning, when people do data exploratory data analysis, they like to use this, right? And usually it's for small data, but if you do have large data, can we use it? You know, people still can try to do something like this, right? Make one leaf represent 10 or 100 or 1,000 pieces of data, right? Usually, if you use software to do this, right? So while you're making this chart, ask software to do this. It'll put a note underneath, say, 1 leaf stands for 1,000 records or 100 records. You'll see that. Okay. So that's stem and lead plot. Another important chart that people do is graph is histogram, right? The bar chart for quantitative data. So for doing that, you first have to organize your information. Okay, so for categorical variable, we have just limited number of categories, few categories. Like a gender, we have only 2, right? So each category, we can count how many data in there. But when you have quantitative data, you have so many different values. Right? Just generally, people don't make a frequency table to record information for each value. Okay, so what people do is set up intervals. So quantitative variable, we set up intervals to organize these information. So we have data actually range from, I think, 100-something to 280-something, okay? And then we have 22 pieces of data. I think you saw that data last time, right? I collect from students. So what I did is actually split that range into here, I think around 10 intervals, right? With the size of interval, each one is like 20, right? So anytime you have data between 100 and 120, I put it in this class. And next, between 120 to 140, I put it in this class, right? So I can set up these so-called classes, right? And each class, they have a lower bound and upper bound. Okay, what I did here, actually, I have lower class 100 inclusive. That means if you have value that's 100, I'm going to consider that's in this class, right? But right end exclusive, I'm going to include 120. I'm taking anything less than 120 and above 100. Okay, So any data in that range, I count 1 here, right? I will count it here. And I do that for those data, and this is what you see. If you do it by hand, right? Just 135, that's in this range, you put a bar, and 119, you put a bar here and keep going if you want to do it that way. Okay, but eventually, you'll be able to count, right, the frequency for each class. Doing this, you won't count a piece of data twice or in 2 classes, right? It's very clear. You don't want to say 100 and 120 and 120 to 140, but when you really try to do it, you don't know. If you have a piece of 120, you don't know where to put it, right? This is very clear. Right? If it's 120, it goes to this next class. Okay, it's simple. But you see some of the, especially textbook, right? Some of the author actually trying to play with the boundary. They say, 100 to 120. How about I put 100 and to 119.95, right? So if I have the data, I note exactly which class to go. Okay, that's good, but it's just too confusing, right? It depends on how many decimal places you have, and so that's too. This is easier. Okay, so I like this, and fortunately, I think our textbook also take this approach, right? So that's probably one of the reasons I picked that book. So that's easy, right? This is very simple. So you get your frequency distribution like that, right? And then most of the data in this range, and again, there's an outstanding value here, okay? Sometimes, if you have really extreme outliers, sometimes people will say 280 and above, right? Try not to stretch that, that interval to too many intervals, right? So people do that, okay? And also, once you got your frequency, we can also divide these frequencies by total to get the relative frequency, like what we had for categorical data, right? Relative frequency is like percentage. Okay, and so once you got that, you get a so-called relative frequency distribution or percent distribution of the data. And sometimes people also do the so cumulative relative frequency. That is the total relative frequency accumulated at the end of each class. So in the end of this class, we have 3, right? 3 out of 22. That's cumulative distribution here. End of second class, we have totally 6 accumulated. So this is cumulative frequency in the second class, and so forth. So at the end, you're going to have all 100% accumulate. So at the end, this, the relative frequency, cumulative relative frequency is going to be 1, right, or 100%. Right? So this is called cumulative relative frequency. Right? That's easy. So these are the terms I kind of mentioned. Each class I set up for quantitative variable, there are intervals, and frequency is like a count, right? And we have relative frequency is proportion or percentage. Okay, so when you make those tables, you will have class set up, and then you count the frequency. You also get the relative frequency. So once you have that list of frequency, you have a frequency distribution of the data. If you have that list of relative frequency, then we'll have relative frequency distribution of data. That's just terminology. I hope you know, right? Just in case you have to communicate with other people. And the highest value that can go into one class, we call it upper class limit, and lowest number that can go into a class, we call it lower class limit. So that's easy to understand. Size of the interval is called class width. Okay. Midpoint of the interval, sometimes we have a name, we call it class midpoint or class mark. Sometimes people use a midpoint information in the chart, midpoint, to show some information or make charts, right? Sometimes people use that for estimation purpose. We'll see that later on in the course, right? So class midpoint has a reason in there, okay? So we made that table, and these are the principles, right, that people use in making those frequency table, and organizing, displaying quantitative variable, right? Because you have so many different possible data, so you have to set up those interval classes. How many classes should I use? Usually, you don't want it to be too many classes, and it depends on how many pieces of data you have, right? So general guideline is that it should be between 5 to 20 classes. It depends on sample size, how big a data you have. You only have 5 pieces of data, it doesn't make sense to have 20 classes, right? So it really depends. And each piece of class data, of course, should go only into one interval. Okay? And when visible, all classes should have the same width. So when you display a chart from the data, right, the graph will make more sense. Okay, be easier to make and also make more sense. There are ways to actually use uneven interval to make histogram or display information. I personally don't quite like it, right? But for basic statistical analysis, we don't really need that. But anyway, so these are basic guidelines, and we kind of follow that guideline, okay? When we do it, we actually make a table with first, when I say that, I look at the range of the data, right? It's from 100 to 280. Because of that, I know the range. I kind of do a try and error. If I tried class with 10, that give me almost 20, right, classes. That's a lot because I'm 22 pieces of data. So how about I make it class with 20? So you give me like about 9 to 10 interval. And that's good. I have 22 pieces of data. Right? That's probably good. Right? So that's how I did it. Try and error. Okay. I try a class with 20 and give me about 9, a number 9. So I'm going to get probably 9 or 10 intervals. That seems okay. That's how I decided the interval. Okay. There's if you're a computer science major, if you're a programmer, not necessarily a computer science major, and you write a statistical software or other software try to organize information. And oftentimes we like the software to be able to automatically determine, right, how many intervals we have there. Right? And Sturgeon actually developed a rule. We call it Sturge rule. Okay, that actually can help us automatically determine how many interval we need to use for a range of data. So how is it? What is it? The Sturge rule is K is number of classes I use. Right? It'll be 1 plus 3.322 times log base 10 of n is the sample size. So if you know your sample size, using this rule, it helps you to determine how many classes you need to use. Right? So for our data, we have actually 21 pieces of data, log base 10 times 3.322 plus 1, you get 5.4. So in this case, you probably will use 6 classes, right, based on its suggestion. But when you're trying to make this information, display this information to people, you want the information easier to read or easier to understand. Usually people like to have multiple of 10, multiple of 5, multiple of hundreds, right? Instead of having like 6 or 7 as a class width. Okay? So it depends, but most of the software allow this rule in there to automatically build or determine number of classes, and you also allow to, most of the software you can adjust the class size. Right? And some of the software actually, they try to choose a possible multiple 10 or good multiple, right? As a size and as an interval size, right? To make the charts more much easier to read. Okay. So, but anyway, there is rule just in case you like to know that. I won't test you on this, right? So don't worry about it. Okay. But there is something that can help you to automatically determine number of classes you need to use. Okay. So anyway, let's get back to that. So earlier I used 100 to less than 120. Can I use greater than 100 to less than 100 to 120? Yes, you can do that. Right? This would be left end exclusive and right end inclusive. That's fine. Generally, if you have very large data, the difference won't be big. Right? Either way is good. I think most of the software using the first approach, right? Left end inclusive and right end non-inclusive. Okay, so the result actually is very close. So you have a lot of data in this range and only one piece of data outstanding, right? So that's okay. And after that, well, this is the table we had earlier. So you see the difference? Not quite big, okay? Especially if you want to understand the distribution pattern. The difference is not really huge, okay? So after that, then we can use that to make a chart. This is called histogram. Right? We have number from 100 to less than 120. How many of them? We have 3, okay? So we have 3 count, and next column we have 3 counts. So when you look, this is a chart made by SPSS. You see that you immediately know how they determine the class. Okay, so you see a pattern look like this, most of them in this range, and then one piece of data on the right-hand side. Now, usually, when you look at a quantitative measure like this, like weights and heights, like your GPA, ACT score, a lot of times you look at these data, the distribution pattern of the data look like a bell shape. Right? You probably have studied, right, some property of normal distribution or bell-shaped distribution. Most of the time you see that, okay? So here we're studying weight. Usually you should see a bell-shaped pattern, okay? But you don't see a bell-shaped pattern here. There's so many reasons. One is you have very few pieces of data. You only have 22 pieces of data, right? So that sampling variability, okay, make the outcome doesn't look quite like the exact distribution shape of a population that the sample is coming from. Right. How large a sample will make this chart more realistic or closer to the actual data, or actual distribution population? Usually it will take more than 100 or 200 or 300. Right. Larger sample, right, will help you to understand a little bit better. Okay. So here, you don't see a bell-shaped curve. That doesn't mean that data is not from a bell-shaped distribution because of sample. That's one thing. Also, if you look at the data, it actually go up and then down and up and down. Right? So there are kind of two humps there. Right? When you look at a variable, a lot of variables follow a bell-shaped distribution. Most of the people in the center, and there are only a few people on each end. Like you talk about IQ, right? Most of the people around the average IQ, and there are a few people that are extreme on both ends. Okay. When you look at the weight, it should be about the same. Unfortunately, we don't see the same situation here. Okay. Who can tell me why? Possible reason? If really we saw two humps. That's really the reason, right? One significant, important reason. There may be other reason, right? But this is actually a reason, okay? Male had a bell shape, female has a bell shape, right? And when they meet together, you have to have bell-shaped curve, right? So that's really, in this kind of situation, most likely that's a reason, right? So sometimes when you make a chart like this, it can help you to understand a little bit more about the data, okay? Here is one application of midpoint. You can actually connect the top of the bar, right? Midpoint on top of the bar. That's a class midpoint, right? And then connect them together to get the so-called polygon. Right? So this is a polygon for displaying the relative frequency or frequency distribution of quantity of data from histogram, right? So if I remove those bars, I got a polygon, right? So I guess that's easy to understand, right? The cumulative relative frequency, we can make a chart on that too. You can draw a bar chart, right, or histogram, but this is cumulative relative frequency histogram. So the height of a bar represents the cumulative relative frequency, right? At the end of first, we have 3 out of 22, and then end of second, I have 6 out of 22, and so forth. Keep it accumulating. Okay, so that's a cumulative relative frequency. A lot of times people use cumulative frequency to actually checking distribution pattern. Okay, you could have you believe that data follow a bell-shaped distribution, okay, and you want to see whether your data really follow a bell shape. So you can draw a cumulative distribution of bell shape and then cumulative distribution from your data to see they meet, right, or they match pretty well or not. There are some statistical inference procedures that are developed based on the idea of cumulative distribution. Okay. So anyway, the more you learn about statistics, you will find out some approaches actually take on using the relative frequency approach, cumulative relative frequency approach. But let me just give you one example. Suppose you want to find the 90th percentile. Quickly get an estimate of 90th percentile. This chart will help you a lot, right? If you want to do a 90th percentile, draw a line at 90%. Find an intersect. That point is likely your 90th percentile of the data, right? Does it make sense? Okay. So that's one application. Right, so 90th percentile here is approximately like a 200, maybe 13 or something, right? Okay. So anyway, so what do we see in? You should try to look at in the histogram. Now, it's a quantitative data. So sometimes we use histogram to see whether there's outstanding data or not. Sometimes outstanding data is error. So you want to correct those errors, right? Sometimes outstanding is really accurate. It's real data. It's just your distribution just have chance to get outstanding data, right? But you got to know that, right? And center, usually when we do comparative study or understand the typical location of a distribution of data, we look at the center of the data. Okay. And spread, we mentioned spread last time. Larger spread, sometimes it's good, sometimes it's bad. Anytime it comes to quality control, large variable is not good. Okay. So you may have two histograms from two process, manufactured process, right? For manufacture certain product, and you have measurement from that. So one is large, one is small. That means larger, it has worse quality than the smaller one, all right? Or narrow one if you look at the shape. And the shape means different distribution pattern. Sometimes shape could be flat, sometimes shape could be bell shape, right? Sometimes shape may be skewed. Let me show you this. Right? This is a typical distribution that we usually see, bell-shaped distribution. You look at the heights and weights and test score, right? Sometimes you may have distribution look like this. You have a long tail on one side. That's possible, okay? And there are some well-known distribution, right? Mathematical model that can be used to categorize or describe this kind of distribution, and can help you to do data model related to this type of distribution, okay? Now, what kind of distribution is likely to have a skew, right skew? A lot of time, you know, lifetime of a TV monitor, okay? Lifetime of a light bulb, okay? Waiting time until a certain thing to occur. A lot of time you follow this kind of distribution. Price of house, property, a lot of time follow this distribution. Salary, a lot of time follow this distribution, right? If you look at salary of a company, most of them are in this range, but there are a few executives that are way high, okay? Look at the property value. Most of the property value are in this range, but there are a few multi-million houses. Always that happen, right? So you have skew to the right distribution, right? And this is called skew to the right, right? Whichever side you have a long tail, we say distribution skew to that side. A lot of times students misunderstood, thought that, well, you have a lot of them on the left side of this distribution, so you say skew to the left. That's not right, right? People say long tail, that side is a distribution, a direction your distribution skew to, right? So this is skewed to the right. Sometimes we say it's a positively skew, right? In the real number line, right side is positive, right? Left side is negative, right? Okay. So I hope that makes sense. And bimodal is something that we just saw. Right? You have two modes there, right? You may have trimodal. It really depends on the situation. Okay. Uniform means the distribution is flat, right? Regardless of what value, the chance of each of those values are the same. Like the number you use, outcome from the lottery game. Supposedly, every number should be equally likely to occur, right? So a situation like that is uniform. That makes sense, right? Okay. And of course, you have skew to the right. Sometimes you have skew to the left, right? So these are different distributions. And mathematically, right, for these different type of distributions, usually we have some model we can use to categorize or describe this distribution. Okay, so we will see that later on in the class. Any questions? Right, so this is a shape, right? You usually like to know that too, because second part of this class we talk about statistical inference. And a lot of these statistical inference procedures are based on some distribution model, right? We assume that our data is from this type of model, right? Then, okay, this procedure can be used, right? So a lot of models are based on different distribution, underlying distribution, right? So you got to know that before you can apply those procedures. That's why it's important to understand what kind of distribution shape we have there. This is a chart that I saw from internet about that histogram had a mix of, this is actually height, I think, probably not weight, that's height, okay? So you measure the heights for all the students and line them up, right? The shortest here and tallest here, okay? Here is a mix of male and female. It's hard to see, but you look at this picture. Y is female and black is male, okay? You see that, right? Okay, good. So histogram, right, it's a very useful chart for us to understand quantitative measures. And usually you see a histogram, you kind of know the distribution pattern, and if you know statistics enough, right, you'd be able to actually maybe make a polygon, right? I try to see what kind of distribution function that would match this kind of model. Okay, so that's usually that kind of distribution function, we call it density function. Right? Over here, in the center, we have a higher density, right? We have more people in this range. And when they get further away from the center, we have lower density. And we can come up with a mathematical formula, right, that hopefully can describe this different density of the quantitative variable, or distribution of a quantitative variable. Okay. So keep in mind this density function, right? It's a function of describing the distribution pattern. Right? We will look into that later on in the course. Usually it's a smooth function, right, and fits your data very well, right? And we use the area under this curve to help us model the distribution. Right? We'll look at that in a little bit. Okay, so that's histogram. right? A histogram is a bar chart, just like a bar chart for categorical variable, but we have a term histogram. So remember, for quantitative variable, you use histogram. So when you use software, software has an option, bar chart and histogram. If you want to display quantitative variable, you have to choose the histogram option. Don't choose a bar chart, right? It's going to look weird, right? Okay. And box plot is another chart. This box actually, look at the vertical axis. This is a scale, right? So we have height variable. Want to display the spread of the height variable. This box, lower edge and upper edge, indicate the 25th and 75th percentile of the distribution. And this thick bar in the middle indicating the median of the data. Okay, and they are whiskers. Sometimes people call this box and whisker part, right? So these two ends are whisker. These two lines extend to the maximum and minimum of the data. Okay, that's a nice chart. A lot of times people try to understand or study quantitative variable. They like to, especially comparative study. People like to use the box plot. We will look into this later on, right? When we review the percentiles and so forth. Okay, so that's about univariate analysis. When you have data come in, right, the first thing you will do is univariate analysis, right, and do descriptive statistics for it. And if you have software, that can be done very quickly. But you have to do that, right? Don't get the data and run any analysis right away. You'll be in trouble because remember there's a piece of data 6 there, right? If you didn't get rid of that, your answer is actually useless, right? Big error in there. And in statistics, most of the time we do the bivariate analysis, right? Examining correlation between variables, right? So that's called bivariate analysis, examining relation between two. And this is an example of examining the relation between two categorical variables. I think we saw one earlier, right? Drug and hypertension, okay? This is about smoking and cancer, okay? So we have actually totally 100 people, 50 smoker and 50 non-smoker, and we record how many of them have lung cancer, and we got these results. Okay, so this is, we call it contingency table, right? You cross-tabulate your information, okay? And usually what you will look at is this, the distribution row-wise or column-wise. In this case, I would look at it row-wise. I want to see whether there's a correlation between smoking or not versus cancer or not. So we'll look at the distribution for smoker. Their cancer and non-cancer distribution is 20-30, right? But for non-smokers is 5-45. So 20-30 versus 5-45. The distribution is quite different. Right? This is 2-3. This is 1-9. Okay. So if you see big difference in the distribution pattern between these two rows, that kind of indicating that there is some correlation between smoking status and lung cancer, right? Right. If there's no difference, right? You have 2-3 here and 2-3 here. It means whether you smoke or not, right? Your risk of cancer is about the same. Right? So this is a really nice table for organizing your quantitative variable, right? Two quantitative variable in a way so that you can see the correlation between two variables. Okay? And oftentimes what people would do, this is one thing people do, right? We calculate odds. This study, actually we call it retrospective study. Okay? And for smoking, this kind of research, that's usually the only thing you can do. At this time point, I observe these people, how many of them smoke and how many of them don't smoke and didn't smoke, and what proportion have cancer and not, right? And so after thing had happened, that's the only thing we can do. We cannot do the so-called retrospective prospective study. That is actually, that's a term people use, right? That is, at the particular time point, you collect these person and you randomize, right? Assign some people smoke and non-smoke and observe them a period of time and see the outcome. This is called prospective study, right? This is actually, evidence from there is scientifically more sound, right? But generally people don't do that, right? For smoking, retrospective is usually what people do. And when you're doing retrospective study, these odds are usually the stats that people use, right? What is odd for cancer among smoker? That actually is ratio of percentage of cancer versus non-cancer. That's called the odds of getting cancer for smoker. Am I making sense? Right? So that's like 20% versus 30%, or 20 versus 30. So that's 6-9. That's about 2/3. That's the odds of getting cancer for smoker. For non-smoker is the ratio of this versus this. So that's 1-9. odds is not probability, right? Remember, that's just ratio to probability, right? Getting cancer or getting disease, right, versus not, okay? And sometimes when people get these two odds, they will calculate a number called odds ratio, the ratio of these two odds. It will give you an idea whether smoking is a good thing or not, right? Over here, you see the odds ratio for smoking versus not smoking, right? For getting cancer. The odds ratio for the smoker and non-smoker is, what, 6. That means if you're a smoker, your odds of getting cancer is 6 times than those non-smokers. Okay, so that's a really useful and good statistic that people often use when you're doing the risk assessment, the risk analysis. Okay, and based on information for contingency table. Right? So that's for studying categorical variable. You have 2 categorical variables, you want to see the correlation between them. Okay, and we can also make a chart for that. This is called cluster bar chart. Okay, sometimes people call it, there's so many different names, right? Sometimes people call it comparative bar chart. Okay, comparing 2 categories of outcomes, right, for 2 categories of subjects. Right? So here you look at this. Those for the smoker, right, for their cancer non-cancer rate, the distribution is this blue one. For non-smoker is the green one, right? So you see the distribution pattern not the same, right? If this, I'm using percentage. Usually you like to use percentage, right, when you're doing these charts. Now, if I see this green bar is about the same height as this, and this green bar is about the same height as this, that means what? Whether you smoke or not, right, your cancer, odds of cancer is about the same. The distribution of cancer or not cancer is about the same. That means there's no correlation. Right? So a chart, we call it cluster bar chart or comparative bar chart, is very good for understanding the correlation between 2 variables, categorical variables. Okay? Very useful. Some of you, a lot of students actually use that for their project, right? When they do the observe the categorical variable. Okay, so that's 2 categorical. How about 2 quantitative variables? Here is a temperature versus mortality index. Right? This observed from almost 20 countries. Right? So there's one country temperature is average temperature, annual temperature is 34, and mortality index for breast cancer is 52. Right? That's one country, and each subject or each country we observe 2 observations. Okay. And we want to see whether temperature and mortality index, is there any correlation? And how do we do that? By graph. We can actually do a scatter plot. We know how to make scatter plot, right? We have order pairs. Okay, so here, the average temperature will be x coordinated, and then mortality index will be the right coordinate, right? So you plot these order pairs, you get this so-called scatter plot. And that's a very useful chart, right? To understand the correlation between 2 quantitative variables. You see a pretty clear trend here. Okay, when average temperature gets higher, the mortality index gets higher. Okay, so it's a really nice chart, right, for understanding the correlation. Okay, so either one of these examples. This is for 2 quantitative variable, and this is for 2 qualitative variable. Right, they were all really good, right, for understanding the correlation. But an important concept in statistics from this course you definitely want to know to avoid saying something stupid in the future, okay? When you see correlation, that does not imply causation. That's a very important concept. People usually misunderstood that, okay? For instance, this cancer and smoking and cancer. This is from observational study. We just observed. Okay, we found strong correlation. It does not imply that smoking really causes cancer. Remember, I mentioned some tobacco company actually commented that well, it's a gene, it's not smoking. Okay, unless the data collect from a properly designed experiment, right? So you're conducting an experimental study, and the outcome showing you this, then your evidence be strong. Okay, if it's just from an observational study, you don't want to say smoking causes lung cancer. Don't want to say that, all right? You have to do more. Well, for this quantitative situation, the same. Every temperature gets higher, seems like mortality index gets higher. Does that mean that high temperature causing high mortality? If that's the case, people don't want to live warm area, right? It's not the case. In this situation, you just find out that, well, those countries who are in warmer temperature area, most of those countries, they're not well-developed country, right? They have less medical facility or health education, and all these other factors actually is affecting the outcome. It's not really the temperature. So you cannot say that temperature causes the, right? Am I making sense? Okay, so that's very important concept. But of course, when you see a trend, usually we can build a model, right, from the trend. So in the future, you can use this strong correlation outcome to build, use that to support your model, right? So you can build a model once you see the strong correlation. Then use that model for prediction purpose. So next time if you see a country whose average temperature is about 50, then you say, oh, the mortality index is probably around 100 in that range because of this trend that you see there. Okay, but you definitely don't want to say temperature is causing the mortality to be index to be so high. Okay, so that's very, very important concept. Okay. Okay, so here are a few terms that actually people also often use, and they are important too whenever it comes to study the correlation between two variables. Oftentimes, there is a reason that you conduct your research, right? You observe some strange phenomenon. You observe some outcomes that you feel uncomfortable. You want to see what causes it or what actually leads to these results. Right? So, for instance, you found a lot of people get lung cancer, right? And you think that's outcome for something. Okay, so lung cancer, you believe it's outcome from something, then lung cancer is so-called the outcome variable. Or sometimes people say it's a response variable, okay? Or dependent variable, because it depends on what, this outcome depends on some kind of behavior, right? So this is, again, some terminology you like to know, because if you know the terminology, also it helps you to understand the concept, it also helps you to use the software, because software will use these terminology, right, when you try to do the analysis. And of course, another variable, if you have two variables, if you study correlation between two, the other, one is response and one will be what? Explanatory variable. Sometimes we call it independent or predictive variable, okay? So for lung cancer situation, smoking is an explanatory variable, okay? Or sometimes we call it independent or predictive variable. If you smoke, you're more likely to get cancer. If you don't smoke, you're less likely to get cancer. You can actually use these data to build a model to predict the probability of getting cancer also, okay? But before you do that, you got to know these terms too, right? They're simple. I think they're easy to understand, right? Good. So we have correlation between two categorical variable and correlation between two quantitative variable. What if one is qualitative, one is quantitative? This would be the situation. We have gender, that is categorical, but we like to understand the difference, right, in height among these genders. So if we believe that if you're in different gender, your height will be different range, right? So there's some correlation. And this is one chart, one good chart I can show whether there's correlation or not. Here, if you're male, your range is like higher, right? Especially your 25th percentile and the 75th percentile is in this range, right? But for female, it's in this range. So you kind of see the difference there, right? This is a nice comparative chart by comparing quantitative variable among two different categories of subjects, right? So we'll look into box plot in a little bit, right? I think a lot of you probably have learned these. Right? How many of you have seen bar chart or make bar chart, box plot, before? How many of you have done that? Right, a lot of you have done that. Right? So it's a very useful chart. Right? I believe in the future, if you do some research doing data analysis in comparative study, right, you would do something like that. So what if I have not just two, more than two variables? And it also happens all the time, especially if you're trying to do observational study, right? And in the real world, actually, there's a lot of observational study that we need to deal with, because not all the data or study you can do experiment, okay? So you got to examine correlation between so many variables. Remember, we talked about the drug use and then hypertension, right? We like to study the correlation between the two, but we believe age is also a variable. Age is affecting the outcome. So you want to include age in there, right? So that first example I've shown you last time, right? Or actually first day probably. That's a multivariate. Now, age may not be good enough. You may want to involve gender, right? You may want to involve level of education. So that actually is very involved, right, situation. Well, we'll see that later on, right? But that's multivariate. This is the chart, actually, a good chart displaying showing multivariate analysis. We have precipitations and minimum temperature and hospitalization from pneumonia, right? So this solid line is report from pneumonia, and these big dots is actually the precipitation, and the small dot is actually temperature, right? So you see the hospitalization get higher when actually precipitation get higher and temperature get lower, right? So it seems like there's a correlation, right? Precipitation and then temperature, both kind of affecting the number of hospitalization from pneumonia. Okay, so that's a good chart. People actually, a lot of people still doing research and try to develop charts for help us to visualize the situation, especially multivariate case. Okay, so it's very interesting. Okay, so that's a good example. Let's look at another possible situation. We need chart. Time data. When you have data related to time, right, you do so-called a time plot. Okay, so this is an example of time plots. I have a crime rate from 1995 to 2010. Okay, so each has a rate, so we can actually horizontal axis of time, and then you start plotting these rates, right, 1 year at a time. Right, so that's actually, this is out of all. Then you can see a trend of the data related to time. Right, so that's easy. I think you saw that all the time, right? That's a time plot, so you see a trend there. Okay. This is actually when I first few years when I came, there's a professor from criminal justice. He wanted to learn how to use SPSS, so he gave me the data, asked me to actually make a chart. He wanted to present a talk in the conference, so he needs to do some graph very quickly, and SPSS can do a good graph so quickly. Right? So I just made a chart from it. So this actually shows us what's going on according to regarding to homicide rate, right, in Youngstown. So it seems like pretty flat, right? It's among like 15 to 30 in that range, fluctuating until 1990, and then suddenly jump to 60, and then go down a little bit and up. Right? How many of you from this area? Most of you are from this area, right? 1969, you're not here, right? So you probably don't know the history, what's going on, right? I came 93, right? So I came 93, went down, right? So I have good influence, right? It's not because of me. But there got to be something. So this time chart actually tells you a history of what's going on according to homicide rate. So that's actually a good chart that people use all the time. Right? Now this is interesting. So I got the national homicide rate from him too. Okay, and we made a chart like this. When I saw this chart, I said, "Oh wow, how come? There's not much change." Okay, and but we want to display this chart in a different way because the scale here is from 0 to 100. Okay. So we want to display a little bit, and we'll kind of see, because most of the data is between 0 to about 12, I mean, between 0 and 10. So I made another chart like this. Now, if you view these two charts from a distance, wow, they're a different thing, right? This one actually shows more fluctuation there. This chart, less fluctuation. Is any of the chart that are incorrect? No, they are the same thing, all right? This is a thing that you have to pay attention. Every time you read a chart, you want to read the scale. Okay? Otherwise, you'll be misled to something. If this is like police department, they try to apply for grants, right, from maybe a government for state. They may want to show something like this, right? There's a big jump and there's fluctuation. We want to have better control of crime rate. So please give us more money, right? So we can do a better job, okay? But if you want to tell that some people that we're doing very good in this area, right? The police are doing really good job in this area. There's not much change in crime rate. We're maintaining this low rate. Then you will show this, okay? But if you are the reader, you're making decision. You got to be careful, right? There's nothing wrong. There's no misleading thing, anything there, okay? There's no incorrect statistic there. It's just using different scale. Right? So if in order to make decision, you have to just be careful. Right? Look at these two. Actually, this is from a case study that people complain that there is sexual discrimination, right? So they're trying to figure out how many female employee and how many male employee in the company. So these two charts tells two different stories. Okay, this one kind of say, well, female is a little bit low, but not so much different. But this one actually is huge different. But if you look at these two charts, scale again is different, right? Here actually is with the reference point 0. Here you're starting with 210, right? Just try to exaggerate this range, right? So again, if you're the decision maker, you need to be careful, right, while reading this chart. Okay, make sense? There's no error in there. It's just how you emphasize or de-emphasize the situation. Okay. Here is a chart that is not good. It's incorrect. Different company like try to compare their sales. Right. This is a magazine talking about the sales. Well, actually, customer service advertised, internal money. Right. They are trying to show this money amount. And the height actually is reflecting the difference, right, the actual money amount. But when they use a pen and they try to enlarge this pen, they actually stretch in 2 dimensions. So actually make this pen is probably, the height of this is probably maybe a little bit, no more than 100%, right? But if you expand it in 2 dimensions, this pen actually more than twice the size of this. Okay, so be careful. You can use a pen with the same width and stack, right? And to make that outcome more accurate. Try not to stretch it 2 dimensions, right? There are a lot of charts like this, and people did it. They're naive. They didn't know, right, that they're misleading people. Right? So be careful when you're making charts. Okay. So we quickly review all these basic descriptive statistics. Right? I think you saw this before, right? So it should be easy for you to do these problems. And I gave you a assignment sheet